So, good morning. Today we are coming into the measurement part, or actually understanding what we are doing. Until now we have been doing essentially image processing, more or less. And now we're going into understanding what the data actually means. And for that we need uncertainty, statistics, and as supporting technical part, reproducibility is also very important. There is, again, quite a list of books that you can read if you enjoy it. There are some new books, for example here, some on statistics and measurement uncertainties. And before the lecture I actually mentioned this book, Image Processing Under Uncertainty. It's a PhD thesis, where I tried to use the uncertainty in the image processing workflow and even develop extra algorithms for doing it, for handling the uncertainties. Then also a bunch of papers on or websites on different parts of the error propagation, detection limits, etc. And finally, some videos, podcasts, some serious, some less serious. So the entertaining ones, they are more for entertaining, quite fun to watch actually. So one is John Oliver telling quite some interesting statistical studies, and the other one is about why you can sit in a boat in Minecraft and fall down the cliff and survive. Also about uncertainties actually. So what we have done until now, as I said before, we have essentially been doing image processing and looking at first preparing the images, extracting features, measuring these features, etc. But we haven't done any statistical analysis on it to make a conclusion. And that's where we are going today. First, giving some scientific goals. The first part today will be a lot about uncertainties, and then we switch over to statistical methods and some reproducibility. And the thing is, we have been talking about, so this class is about quantitative big imaging, but until now, we have only talked about the image processing, not really about the big. So what does really big mean? A definition in big data is that to be handling it, you will have to be ready for big data, so you have to be able to handle large volumes of data. Now the definition of what large volume is very different. For the data scientist, large volume, if it can stay in a rack, then it's fine. But for you, it may be not that big, but still it can be overwhelming. Velocity, how much is produced and how fast you can process it. And of course, variety, having large variety in the data to cover the corner cases. And that requires then that you have scalable methods, which are also fast and fast to work with. So you don't have to wait a year to get the results, but also easy to customize. So you can modify it easily with a few parameters, and then you can take a new data set or maybe a little bit different question and don't have to rewrite the whole code base. So let's look into the big imaging part. What we want to do, we want to squeeze a few numbers or plots out of the data sets to describe some kind of structure. And One thing we have already done is all describing the structures, but now we need to make these numbers meaningful. And we have to, in principle, have different treatments and compare if different samples behave differently, either within a sample or even within the same type of samples or even different treatments of the data. And then we may also have to, as a part of the process, compare different processing steps. Also, maybe determine the minimal volume that you can work with to still get a reliable result, because this is actually a very important fact. Measurements are expensive. So if you can reduce the measured volume, then you can actually have a gain, actually economic gain, and also time-wise a gain. So you want to have the smallest reliable volume in your experiment. And then, of course, evaluating the parameter selection, and of course, ensure that your methods did actually do what they are supposed to. So let's see what we have to start with. So let's go back to this original cell image. We have been able to look at, so that's actually a review up to now. We have been able to get rid of the noise in the image. We have been able to find some cells. We have analyzed the shape of these cells. And then if the cells may be touching, we could actually separate them too using the watershed from lecture 6. And we have even some more metrics to characterize distributions of locations. And now we have some few samples, a larger number of metrics, and a very large number of parameters to tune. Depending on what you're doing, it can be just a few, like filter size and threshold. That would be fine, but it can be much, much more. And now is the question what we can do to make it meaningful. There are different ways of doing investigations. So you can have a correlation experiment, which means that you just measure, observe something, and you look for a statistical relationship between different variables. It's very easy to show. Just a single calculation, you get the correlation between different classes. But what actually mostly is done is that you have controlled experiment where you look at causation. So if you have changed a variable, then what is the effect on the outcome? And that needs to be, so it's very difficult to show unless you have a very controlled experiment set. So this comes to different experiments. We have observational experiments where we just observe. That would be the one where we do the correlation of mostly. And then we have the controlled ones where we actually set the scenery and change one variable after the other and check what happens. When we have the observational experiment, we can explore large data set, looking for trends, maybe hopefully, or it could be that we have a random population. It's not always hypothesis driven. You can just walk around there and see correlations, but it's very difficult to see any causation in those experiments. So for example, if we examine 100 people, we see that the blue-eyed ones are 10 centimeters taller. I count to one of them. If we have 100 cake samples, we found there is a 0.9 correlation between baking time and bubble size. Yeah, things like we can observe. But actually, already seeing the baking time, we could already have that as a controlled variable. So controlled, that is where we have very many of our scientific experiments. Then we have specifics of different groups that we have controlled, and that can lead to a causation. So for example, if we have 50 mice with one gene and the other 50 with that gene inactivated, then we can see that the foot size increased by 10%. We can also see if we increase the temperature, that the number of pores in the metal cast increased by 10%. So then we have controlled these variables and can see what happens. Then we also have different distinctions, qualitative versus quantitative. There's actually a slide repeated from lecture 1. So what we can do, both these are from a cultural heritage application. In one, we just did a tomography, reconstructed it, visualized it, cut it in pieces a little bit, looked at it, and saw some conclusions. Or the other one, looking at corrosion in rusty nails, we could see really a coupling between where we have soil and corrosion products, solid metal, etc. And that we could see and quantify, and it's actually an ongoing project now, where we even try to map different elements into different regions of the nails. So the qualitative assessment is often done using some kind of visual feedback. We can compare different expectations on different independent techniques or approaches. And if there are artifacts, how do they affect their output? Also, do the shapes look correct? Are they distributed as expected? Is the orientation meaningful? So these are often the things that we want to do before we start the quantitative analysis, just to make sure on a few samples, seeing that, okay, it makes sense. But then we go on doing the heavy analysis. And for the quantitative, we want to, for example, calculate some specific shapes or distribution metrics on the sample. And we also want to establish a connection between the changed parameter and some metric in the sample and make a conclusion about that. So that was a general part about the ways of how we measure. And now we go into the uncertainties. And uncertainties in image processing is not easy. It's not even obvious in any sense. In some cases, thanks to all the algorithms we are using, it's near to impossible to derive an analytical uncertainty from the measurement. But we do what we can. Anyway, here's a quote from Richard Feynman. And he says, scientific knowledge is a body of statements of varying degree of uncertainty, or certainty actually. Some most unsure, some nearly sure, but absolutely none is perfectly certain. And it actually closes it down pretty well. And if you want some Nobel laureate biography reading, then this is a pretty fun book. He tells a lot of anecdotes, so it's fun. So what we want to have some kind of error bars on our measurements to give the confidence interval of the noise, for example. So actually going beyond the confidence interval of the noise. And because every measurement has some degree of uncertainty. And the uncertainty propagation through these images and the processes and stuff we're doing is really not trivial. Well, then you can do the fun stuff like in XKCD, putting error bars on error bars, but no, not really that. That one actually converges to something. So the question is now, we say error bars, but actually it is a measure of uncertainty that we are talking about, because the error is an absolute value, and you have to know the ground truth to tell the error. And the uncertainty is more in the style of a confidence interval that we say we know that the measurement is within these bounds. And this figure is taken from Christina Gilman's PhD thesis, which is, at least the first part, is quite general, and then she goes into a couple of algorithms that she worked on, I think for medical imaging. So what kind of uncertainties are we dealing with? We have some technical uncertainties in the measurement, and we have field-specific uncertainties. So first of all, we have an uncertainty in the metric that we measure. We have the signal-to-noise ratio. We have unsharpness in images. We have the effects from the image processing, and we may even have some numerical errors in the processing. Then field-specific, when we go beyond the measurement itself, we can have model simplifications, like modeling everything as a sphere, even though it's not a sphere. There can be variations in the population, and also noise in this case is variation in the studied or outliers in the studied population somehow. And we also have different categories of uncertainty. So we have the systematic. They are always reproducible and not needed any statistical analysis. Here we have the rounding errors, uncalibrated systems, even algorithm choices, and so on. We can also have the random uncertainties. So these are statistical fluctuations, natural variations in the studied population, source fluctuations, detector noise, etc. And often when we're talking about uncertainties, it's displayed in this way, like target practicing. So in the upper row we have low accuracy. We can see that we are far away from the real spot. We can have high accuracy, then we are close to the actual spot. Then the precision says something about the spread. So we have low precision, then it's like taking a shotgun and shooting. And with high precision, you do the sniper gun. With low accuracy, the sniper gun is very precise how he hits the target, but not very accurate on the spot. This can also be translated into statistical terms. And here we're talking about large bias and small bias, large variance and small variance. So there is a connection between these terms, and it's good to work with those. Now is the question about counting and measuring. There are different approaches in image processing. Either you count items in some way, or you measure something like the volume, or something like that, or distances, and so on. So with counting, you have discrete countable items, and it's always absolute values, thanks to that. And the uncertainties come from the preparation, how well you have identified the items. And actually, here I say that the area is, as the area of a segmented region, is actually counting how many pixels you have in that region. There are other ways of computing the area, which would be maybe more into measurement. Measuring, then we are talking about physical quantities. So the signal that we get, the gray level that we get, has a physical meaning. And these values are actually with uncertainties. Here comes the uncertainty from the noise and from the instrumentation. And one example would be to extract the mixing ratio from the gray levels in the image. Then looking at the uncertainties, we are also talking about absolute and relative uncertainties. And the absolute uncertainty is that we have an uncertainty of a millimeter, and no matter how far we measure something, so the distance to the moon is many kilometers, and the diameter of a coin is just some few tenths of 10 millimeters. So, and that doesn't give really relation to how uncertain we are. But looking at the relative uncertainty, then we can see that we are how many places behind the zero? Yeah, many. And on the diameter of a coin, we have 5% uncertainty given this millimeter. So you have to also see if you want to use absolute uncertainty or relative uncertainty when you provide it. And the propagation of uncertainty is something that that is defined in the literature, and typically the uncertainty of a function x is just the derivative times the uncertainty value, and that is how it propagates. If you have two variables, then you have the combination of these two, the two variables, plus a correlation term between them if they are correlated or uncorrelated. Uncorrelated, that one, of course, falls out. Looking at different quantities in an imaging experiment, we have all the uncertainties, and here I pull out some of these uncertainties. We have uncertainties originating from the physics. So here we can have physical things like scattering, beam hardening, attenuation, coefficients, how well they are defined. And we can also have uncertainties in the optics and so on. Could also add maybe the source flux into the uncertainty. The source may not be perfectly stable. Then when we go to levels, we talk about the noise, which is essentially how good your source was. So if you have some kind of radiation, it's usually Poisson distributed. So that also gives you some relation. Then we have uncertainties in the gray levels. Depending on how many gray levels you use, sometimes you only have 10 gray levels to describe something, and sometimes you have, say, 65,000 gray levels on a 16-bit image. Depends a little bit. And it's also a question how these are measured from the object. Further on, we also have dimensional uncertainties. For example, the pixel size, which I'm going to show soon. There we have a relation between some real object that was measured and also the size of the object features in the segmented image. And the examples I'm going to show now is how to put an uncertainty on the pixel size, some problems around the perimeter length around something, and finally also looking at the water volume behind the pixel. So the first part is to measure the pixel size, we need to have two things. One, an object with known length, and an image of that object. In some cases, you just get this pixel size number straight off from the literature or from the manual. But in other cases, when you have an optical bench where you set the field of view between the experiments, this is a very important step. So the pixel size is essentially the object length divided by the number of pixels between two edges in this object. And the uncertainty equation looks like this, where we have the ratio of uncertainties, and well, that is how it's defined. And if you want to look into the detailed steps of that, I have made a tutorial that you can take a look at. in a different context, but if you want to look at it, how it works, also the image processing steps that I did to achieve it, then it's there. So what we have is a test object, and what we do is taking the caliper, measuring this little black piece here. It's very absorbing and it's very thin, so you don't get much edge uncertainty. And then we make an image and measure the distance between the two edges with, within the image. And then I get some different measurements. The caliper had an uncertainty of 0.05 millimeters, and the pixel distance I could measure with 0.32 pixels uncertainty. So it's pretty precise that I managed to produce. And then we plug that in, and we see that our pixel size in this case, so it's in principle just writing this equation, and the pixel size turns out to be 43 microns plus minus 0.11 microns. And this is kind of messy to look up all the equations, etc. So of course someone else had the same problem, so they actually developed this uncertainty package in Python, where you can define uncertain variables. So you have a U float where you set the measured value and its uncertainty, and then when you do the calculations, it automatically computes the uncertainty for you. So that's pretty convenient, in particular when you do more complicated calculations. So if we do measurement in segmented images, we saw in lecture 5 that we could measure area, perimeter, positions, distances, etc. But and these were then considered only as absolute value from counting pixels somehow. So let's see how the pixel size uncertainty affect these measurements. The first thing is we have different on the parameter length. We have different sources of uncertainty. First of all, how was the pixel edge pixels identified to compute the parameter? Here we come into different choices of methods, and then we have the pixel size, and of course finally the segmentation and edges. And when you do segmentation, in particular when you have unsharp edges, that is actually the place where that has the least confidence, as we will see in a few slides actually even. So let's say that we have identified the edge using an erosion approach. So we just take the edge as the image minus the erosion of the image with some structure element. In this case, I used the four connected neighborhood, and you can see that the gray points here, they are the segmented edge pixels. And well, the next task is in principle just to count pixels. So let's count all these pixels, and we get 18. But this is not the only way how you can define the parameter. Still using the same edge pixels, we can also define the surface or the parameter as edge facing background. So that would be along this green line, and then all of a sudden we get 24 as the length of the edge. The next thing would be that we do the center line through these pixels, and then we get 20.5. So depending on how you define it, you can get different parameter lengths. And there are even more refined ways where you can do some kind of polynomial or spline interpolation to get even more precise. But yeah, there are many ways how you can define this parameter. And let's say we trust the segmentation and we use the pixel counting way. Then we see that we got an edge which is 18 pixels long. And now we have the pixel size which we have an uncertainty on. And now we just want to compute the uncertainty of the parameter. And that's pretty simple because it's just summing all the contributions. So it's essentially just multiplying by the number of pixels. And then we get that the edge length is, or the uncertainty of the edge length is about 2 microns. So that gives us that our edge is now 774 plus minus 2 microns. So this is how we can propagate the uncertainties of these values. A more complicated thing, which introduces more problems, is to measure the volume of water, or actually doing an estimate based on the gray level in the image. Here we go back to, what was it, lecture 4, I think, looking at the Beer-Lambert's law. This is how the transmission is related to the thickness. So we need to know some attenuation coefficient, and then we have to do a couple of measurements of the reference image and the one with the sample. And then we have a metric pixel area, which is essentially based on the pixel size. So the volume of water that we want to compute is the pixel size squared times this d. And the uncertainties we have is one is the standard deviation of the transmission. So that is essentially noise-based. We have the pixel size. And actually we have one more parameter, which I didn't mention, and that is the attenuation coefficient, which also could have an uncertainty. But I skip that for now. That would make the slide too cluttered. So, to measure the volume with uncertainty, we have some thickness. Here I just threw something in. It's just a play example. So I said I have the thickness plus minus 0.1 millimeters. We have the pixel size, which we already defined. So now we want to know the uncertainty of this equation, and that is calculated like this. And let's plug that in, and we can see now that we have put in the same things, do the calculations, and we come up to some volume of and its uncertainty in this measurement. So, leaving these things where we know, at least, or can measure the uncertainties, there are cases when we can't measure or we can't put any uncertainty directly on it. And there are different ways to evaluate the segmentation of algorithm performances. We have seen it in many lectures already. We have used the confusion matrix, we have used the RSC curve, hit maps. But all these, they require a ground truth. And if we want to get some kind of confidence measure of a segmented image without the ground truth, we have to work a bit. And let's try to get a confidence map without the ground truth. So let's assume we have Gaussian noise in our image. And it's distributed like this. And then if we have image with two regions with Gaussian classes, and we do a threshold, we know that we get a fraction of false negatives and false positives, depending on where we put the threshold. And we can't know if it's true or not if we don't have a ground truth. So let's see what we can do instead. This is an approach that was introduced by Peter Moonen. In principle, what we need to do is to find the probability distribution function using Gaussian mixture models, and then we can normalize these so we have the peaks on the same level. And then for each gray level, compute some weight, which is based on the probability function for that variable for that class. And the weight is just essentially the Gaussian Bell function. And then the confidence for each class is computed as the weight of that class divided by the sum of all weights. And now we can create a confidence map using the segmented image and compute this CI for each pixel. And CI for a single pixel is computed like this. We have, say, the value around here. And we can see that the C1 is, no, C0 is the green one, and C1 is that one, so it's more likely that this one is the one that we should choose. And computing this, we try on a three-phase segmentation. We have three classes, one at average value -3, one at 1, and one at 5. And we assume Gaussian noise with the same standard deviation. And we also introduce some blurring. So we have this image, which is a ground truth. Now in the following evaluation, I'm actually using that as segmentation too, just to be a little bit cheating a bit to get faster forward. Then we have a smooth image. And there you can see that the edges here, they are not perfectly sharp. And then we add a noise, and this is what we try to segment with our threshold. And then we can from that, we can compute the confidence of class 0, 1, and 2. And you can already see that there is some leaking between the classes, so there are some misclassifications. Some actually have very high confidence, also around here. But the important thing is what you can see is that in particular around the edges, we have most uncertainty. And that we can also see here, that the general confidence map is saying that the big step between class 0 and class 2 is the one that produces the most uncertainty. And we saw that actually also back in lecture 4, I think, where we saw that the uncertainty, when you do this three-class segmentation, there is always a little bit of a gap, and that produces this skin effect that I mentioned there. And that is also now here shown pretty well, that we have this uncertainty which could produce the skin. So, when does it matter that we have these confidence map? In high signal-to-noise ratio images, edges have the lowest confidence, and that has an impact for the parameter computations, tortuosity computations, also network connectivity, and also for the volume when you have very small items. For the low signal-to-noise ratio, low confidence on most pixels, actually, and that then we have all the issues from the high signal-to-noise ratio, plus that we have problems of defining porosity, volumes, and also with labeling. So, as you probably already know, low signal-to-noise ratio is something we should try to avoid. We often get it, and then we try to do the best out of it. So, let's conclude the uncertainties that, in principle, any scientific analysis requires that we have uncertainties and are able to put error bars on our plots and analysis. But uncertainty in imaging is not straightforward. We have the physical uncertainties, which we can quantify. The noise can be measured, but then the image analysis precision actually depends on object size to pixel size ratio. So it's always more difficult to measure small objects precise than larger objects. And often the effect of the processing must be quantified through simulations, because many of these algorithms are so complex that it's not possible to derive an analytical uncertainty propagation through the whole chain. Just a simple case, or simple computed tomography. The radiographs, they're pretty obvious, but as soon as you put it through the chain of CT reconstruction, there's so many steps and so much things that are done on the way that the analytical solution is impossible. So in principle, what you need to do is to reconstruct the uncertainties in parallel to the reconstructing the data. And with that, I think it's time for a break, and then we continue with the statistical analysis.